So, welcome to the WISEE 2020 workshop. This is Dr. Amit baghel, and the topic of my presentation is state-of-art technology in space solar power and importance of metamaterial antenna in transmission and receiving antennas. So, what is the space solar power concept? It is simple as beaming of solar power from space to Earth by converting into microwave or laser energy. It was first proposed by P. Glasser. It will help in solving global energy crisis and help to decrease the use of non-renewable sources of energy. It is available almost 24 into 7 and 365 days. And there is no need of large grid as power can be beamed at the location of demand whenever required. Logistic and safety of fuel transmission is curtailed. So the countries and research in this direction are as follows. Japan and USA are aggressively working on this direction with some demonstration in space as well as on ground. China, India, and Russia has interest in this field. Japan's space agency JAXA has demonstrated microwave beaming at approximately 55 meter and is able to transmit 320 to 340 watts of power from 1.8 kilowatts of input power at 5.8 gigahertz. The efficiency is low and is about around 18.88%. And also, the scientists have worked in near field of transmission antenna. They have not gone to the far field, thus not optimizing the huge antenna structure to achieve this efficiency. Then the Naval Research Laboratory in USA conducted its first demonstration of space solar power in space recently with 12-inch square tile module called PRAM aboard an Air Force X-37B orbital test vehicle on May 17, 2020. So this experiment was to study the behavior of the structure PRAM in the space, and more results are awaited. The silent feature of SPS for initial operation capabilities are as follows. Between 10 kilowatts to 10 megawatts from the output of the loop and receiver has to be there, not to exceed 10 billion to an initial space demonstrations capability, 100 watt per meter square, which is a limit of power density at 2.45 and 5.8 gigahertz. Maximum receiver antenna has to be 0.8 kilometer square, which is nearly equivalent to a circular area about 1 kilometer in diameter. So these are the silent features to make SPS for initial operation capability, and this was a study conducted by NRL. So the constraint was maximum space segments mass is around 55 metric tons. So about 37 Falcon 9 or 29 Falcon Heavy launches are required to transport this space segment in the space. Maximum receiver in mass is around 1600 metric tons. So these are the constraints of transporting so much heavy space segment by Falcon 9 rockets. So the financially it has to be seen how feasible it is. So this is the power beaming scenario with different ways: microwave, medium Earth orbit, millimeter medium Earth orbit, optical medium Earth orbit, and optical geo Earth orbit. So here you can see with the microwave medium Earth orbit, the receive power is more compared to other scenarios. So one of the area where the research is open is to increase the power density at transmitting and receiving side without increasing the size of antenna. That is to get maximum aperture efficiency, because size is a constraint in space as well as in the Earth. Metamaterial, which is an artificial material, can be used and is used for clocking, beam shaping, perfect observer, filters. Use of metamaterial will help to increase the power density with the same antenna aperture. So this is one of the example of use of metamaterial with a transmitting antenna. So this is the array of metamaterial, and this array of metamaterial have an refractive index which is varying with the space, with the maximum refractive index at the center and minimum at the sides. So it behave like a parabolic uh, refractor with a parabolic refractive index, thus giving maximum power density at the receiver side. So this is the 2D plot of the electric field at 6 meter distance with metamaterial and without metamaterial. So here you can see in the broadside direction, around 1.3 times enhancement is seen with the same aperture antenna, which is around 210 by 170 mm square. And the power density at 6 meter, if you calculate, is around 52.73 watt per meter square and 88.83 watt per meter square with and without metamaterial. And suppose the effective area at the receiver is around 0.011 meter square. The output power is 0.977 watt and 0.58 watts with and without metamaterial. So there is an increment of 68% in the receive power. Find well, the input is given as 1 watt. So Cauchy plane wave formation is seen after the wave passes through the metamaterial array. So this increase in the electric field or the power density is due to the formation of Cauchy plane wave when it leaves the antenna, because the plane waves can carry more of the energy for the for larger distance compared to the spherical wave. So let's see how much receiver area we have saved with the metamaterial. So for the power output of 0.977 watt as received by metamaterial, the percentage saving in the receiver area is 68.36%. If we take the same effective area, and if we want without metamaterial, if we want 0.977 watts, so we have to increase our area to around 1.68 times than the 0.011. So we have saved around 68.36% for the receiver area with the metamaterial, with the same area. So considering now the real case scenario, suppose the increase in power density we have seen is 68.46, as if you compare from this data. Thus from the table, the peak power density will be 15.16 compared to 9.9 watts per meter square. So if we look at the table here, so the maximum power density at a receiver center is 9 watts per meter square. And if we multiply with this increase in power density, then we will get 15.16 watt per meter square power density at the receiver side. With the maximum available area as constant as 0.8 kilometer square, the receive power will be 12,128.91 kilowatts with the metamaterial, and without the metamaterial it is around 6400 kilowatt. That is an improvement of 89.51 in the receive power with the same area. So we have seen saving in the receiver area with the metamaterial, with the metamaterial put at transmitting side. Let's see how we can reduce further with the parabolic dish reflector at the receiver side with metamaterial kept at the transmitting side. So this is a transmitting antenna, and this is a parabolic, this is the receiver antenna, which is a patch antenna kept for simulation purpose. And the transmitting antenna and the patch antenna, they are the distance between them is 5 meter. And here the transmitting antenna and patch antenna, and there is an parabolic dish reflector. So what is the purpose of parabolic dish reflector is to change the plane wave into the spherical wave, and then the patch antenna is kept at the focus of the parabolic dish reflector to enhance the power density further. So considering this, the power received at 5 meter with and without parabolic dish reflector are given for the input power of 1 watt. So at 5 meter distance with the transmitting without the parabolic dish reflector, it is around 1.206 milliwatts, and transmission antenna with PDR, it is around 2.345. So an increment by 1.944 times in the power received with the PDR is seen. Thus, if you multiply this value with 1.99 with the same area, you will get around 24,136 kilowatts of power for the same 0.8 kilometers of the receiver antenna. So the conclusion of this presentation is that with the metamaterial, we can increase the power density as well as power with the same area. So the increase in power density is around 68.46%. Thus, from the table, the P power density will be 15.16114 watts per meter square compared to 9 watts per meter square. With the maximum available area as 0.8 kilometers square, the receive power will be 12,128.91 kilowatts with metamaterial, then without metamaterial, which is 640 kilowatt. That is an improvement of 89.51% in the receive power, increased by 1944 times with the PDR. Thus, 24,136 kilowatt of power is received from the same 0.8 kilometer square of the receiver area. Thus, we will be able to save a lot of land and resources, and we will be able to get more of the power by beam shaping and by increasing the power density with the help of metamaterial. And the metamaterial are very flexible and lightweight, which can be integrated with transmitting and receiving antenna. So these are the reference, and thank you.